Let's look at some guidelines for finding extrema on a closed interval. To find the extrema of a continuous function f on a closed interval AB, use these steps. First step, find the critical numbers of your function in the open interval from A to B. Critical numbers are where your first derivative is either equal to 0 or undefined. Step 2, evaluate your function at each critical number in the open interval A to B. Third, evaluate your function at each endpoint of the closed interval AB. And then 4, the least of these values is the minimum, the greatest is the maximum. We will do all 4 steps later in this video. Excuse me. For the first few examples, we're going to remind ourselves how to find critical numbers. So let's look at this first example, find the critical numbers for each of the functions. We're going to start out with the function 5x squared minus 8x. Using power rule to take the derivative, f prime of x is going to be 10x minus 8. 10x minus 8 is defined for all values of x, so this derivative is never undefined. We can, however, find out when it's equal to 0. Add 8 to both sides. 10x equals 8, divided by 10. 8 over 10 reduces to 4/5. For this particular graph, you can tell that the original function is a parabola, and so because the x squared term is positive, we're going to have a function that opens upward. Now, it won't be perfectly drawn to scale. I'm just drawing a rough sketch of this. But our function, because it opens upward, we have an open parabola opening upward. Sorry, y'all, I was trying to do a couple things at once, and I'm not the best at multitasking. This 4/5 occurs where the graph hits its minimum. In algebra, you call that a vertex. If you remember the theorem from the previous videos, any relative extrema occurs at a critical number. So this one just emphasizes that when our first derivative is 0, the value of x where that occurs, in this problem it's 4/5, that will be the x value that indicates a relative extrema. Let's move to a different function. This function is going to be a little harder to take the derivative of because it uses product rule, but it also has chain rule involved because of the square root term. Let's take our function f of t equals t times the square root of 5 minus t. Remember that a square root radical can be written as a power of 1/2. Using product rule, when we take our derivative, f prime of t, derivative of t is 1 times the square root of 5 minus t, plus, then we take t times the derivative of square root of 5 minus t, which will be the derivative of the outside, that's 1/2, and then our power after subtracting 1's negative half. We leave the inside alone, times the derivative of the inside, which is negative 1. Doing some rewriting, all of this stuff in the back, this negative 1 times t, that's a negative t. I left this 1 here as a placeholder. The 2 goes to the denominator. This 5 minus t to the negative half, if I carry it to the denominator and change it back to a square root, that gives me a square root of 5 minus t in the denominator. Before I can subtract these terms, I've got to create a common denominator. In the orange ink, I've taken the denominator of the fraction on the right, and I have forced that to be the denominator of this term here that's not a fraction. So if I'm going to multiply in a 2 square root of 5 minus t, this first term, if I use this as my denominator, I have to multiply in a 2 to keep it balanced, and another square root of 5 minus t. Multiplying this out, 2 times the square root of 5 minus t times another square root of 5 minus t, that's 2 times 5 minus t. If you multiply the same radical together, you just get the radicand, or the stuff underneath. And this is all still over 2 square root of 5 minus t. Now I've got a common denominator, so here in the upper left I have 10 minus 2t minus another t, that's 10 minus 3t over my common denominator. At the bottom right of your screen, the numerator is equal to 0 when t is equal to 10 thirds. The denominator is equal to 0, making it undefined if t equals 5. Actually, any value of 5 or larger will make it undefined, because then if you pick a number larger than 5, you start creating negatives. Be careful in your homework that there will give you certain stipulations for your t variable. I forgot to include them in the original problem, but you'll have something like t less than 4, t less than 5. Be careful with that. 10 thirds, that is a value of t that's less than 5. So it turns out 10 thirds is the only critical number for this particular function. We also have 5, but 5's not in the defined domain. Let's move to another function. We have h of x defined as sine squared of x plus cosine of x. X has to stay between 0 and 2 pi, not counting the endpoints. Another way to write sine squared of x is sine x quantity squared. If you actually rewrite it with the power on the outside, it makes it easier to take the derivative, because you can sort of see where the chain rule applies. So let's take our derivative, h prime of x. That's going to be, outer derivative will be 2 sine x to the first. Chain rule, derivative of sine x is cosine x. Second term, cosine x, has a derivative of negative sine x. So this first term required chain rule. This one is just a direct trig derivative. Both of these terms, when written, and I'm going to take the parentheses out just so it helps you see the factoring that's about to take place. 2 sine x cosine x minus sine x. Sine and cosine have infinite domains. You can take the sine and cosine, sine or cosine of any angle. Back in your trig class, you learned it had infinite domain. Now the range isn't infinite, but we don't need the range here. Both of these terms have a sine x in common, so if I factor out a sine x, that leaves a 2 and a cosine x from the first term and a minus 1 from the second term. Sine x is equal to 0 if x is either 0 or pi or 2 pi. 2 cosine x minus 1, that's equal to 0 when cosine of x is equal to positive 1/2. From your unit circle, cosine is positive half at pi over 3 and also at 5 pi over 3. Be careful to note our original domain, our x had to be greater than 0, so I actually have to toss this 0 out of the domain. It is a valid answer, it just doesn't fit the domain. Pi over 3, pi, and 5 pi over 3, those three angles do fit inside this domain. And therefore, let me erase that so it's not as sloppy. And therefore, we have three answers to this particular problem. These are the values of x where you will either see a hilltop or a valley floor if you were to graph the function. In class, we graphed all of them. I don't require graphing calculators, so if you don't have one, that's okay. Remember, critical numbers will mark off hilltops and valley floors. If it's a critical number that makes your derivative undefined, then chances are you've got either a cusp or a vertical tangent line. Let's move to the bottom. Those four steps that were at the beginning of this particular video, we're now going to do those. This is because we're asked to find the absolute extrema of the function. So if you need to go back, the previous video, the very beginning of this video, you'll find the four steps to finding the extrema on a closed interval. This first function at top left of your screen, f of x equals 5 minus x, that's a line with a y-intercept of 5 and a slope of -1. I've got it graphed down here at the bottom left of your screen. The interval that we're given is -2 to 4, and I've highlighted that part of it in red. This is all we're allowed to look at. Our derivative, f prime of x equals -1. That's the slope of the line. Remember that derivative is a rate of change. For this particular interval, -2 subbed into the original function, 5 minus -2 was 7. And you guys told me in class that the value was 7. At the other end of the interval is 4. 5 minus 4 is 1. The critical number was, we didn't have 1. And note this line doesn't have any hills or valleys. That's because this derivative of -1 is never 0, nor is it ever undefined. And that's okay. Lines will always carry that. Lines that represent functions will always carry that property. The largest y value on our highlighted portion of the graph was 7. That's our absolute maximum. At 4, our function value is 1. That's the absolute minimum on this red interval from -2 to 4. Let's move to the function at the top right of your screen. We're going to do the same thing here. There we go. We're going to find the absolute extrema. So we have a function defined as 3x to the 2/3 minus 2x. And we have a really small interval from -1 to 1. That's all right. Taking our derivative using the power rule, we have 2x to the -1/3 minus 2. That translates to 2 over x to the 1/3. You could also write that as cube root of x if you wanted to. First, let's find out when this derivative is equal to 0. Add 2 to both sides, multiply both sides by x to the 1/3, divide by 2, and x to the 1/3 is equal to 1 as long as x equals 1. Note also that in the derivative, there's the potential to have an undefined derivative. If x is 0, this derivative is undefined. Now let's look at the lower part of your screen in the middle. This original function, 3x to the 2/3 minus 2x, we graphed it. That graph came down linearly, or pretty sharply at least. It may not be a perfect line, but it came down, and then it hit at the origin and made a quick turn, forcing a hill. So there's a couple things going on here. When it comes down at the origin, it's not smooth. It makes a sharp turn. When x is 0, notice that our derivative was undefined. At +1, we have the top of a smooth hill. When x was 1, our derivative was 0. So there's a subtle difference there you got to watch out for. F prime of 0 is undefined. F prime of 1 is equal to 0. The difference is whether you've got a cusp or sharp turn versus a smooth hill or valley. Based on our visual, we have a smooth hill at 1, a sharp turn at 0. Look at the very bottom in the blue ink. Because we were asked to stay within -1 to 1, including the endpoints, at -1, and this is back to our original function, if you substitute -1 into the original function and you calculate it carefully, you get 5 as an answer. That just tells us the point -1, 5 is on the graph. At 0, f of 0, your answer was 0, and that just reaffirms that the graph touches at the origin. And finally, at the other end point, f of +1, when you substitute 1 in for x, our answer was +1. And that just tells us at the top of the hill, we've got the point 1, 1. The absolute maximum occurs at the function value where you get the largest answer out of all of them. 5 was our largest answer, so our absolute maximum for this function over this interval was 5. The origin, that's the lowest point, that's the absolute minimum. And then this little hilltop at 1, 1, it wasn't the largest, it wasn't the smallest. It is information, but as far as absolute max and min goes, 5's your absolute max, 0's your absolute minimum for this function in this interval. So you take your derivative, find out where the derivative is 0 and or undefined. Those are your critical numbers. You will take your original function and you'll plug in both of your interval endpoints. You'll also sub in any critical numbers. And then once you've got that list figured out, your largest answer is your absolute maximum, your smallest answer is your absolute minimum.